Assalamu alaikum. My name is Muzan Saud and I am a student of UT Texla. My registration number is 16T49. So in our today's lecture we will study about signal and system. We have already studied the signal and system in our previous lecture, but we will fastly revise this concept. What is signal? Basically, signal is something that we have given to a system so that system performs some operation on it. The input given to a system is known as the signal, and this is all about the signal. And the system is the combination of equipment or something like that, and when we applied some input and it will give some output, it performs some operation. The example I have given to you is electric motor is the simplest example. Electric motor. So we will not waste time on these concepts. If you want to revise these concepts, you can check my previous lecture. Now today's concern is about the linear system, requirement for linearity. We have studied also some important system. The most important was linear system. So what is linear system? Requirement for linearity, we will see. First, the linear system should have homogeneity property. What is homogeneity property? If let's suppose we have signal x of n, we have given to a system and it will produce a result y of n. This is system, this arrow is system. So what is homogeneity? If I multiply this signal, input signal, with a constant k, let's suppose that is k, some constant, maybe 10, 5 or something else, at the output I will see that the output is also a multiple of same constant that I have multiplied on the input side. So this is the homogeneity property that will satisfy these linearity, this condition. Now the second one is additivity. What is additivity? Let's suppose I have a signal x of n and pass through a system and get the result y1 of n, and I have second signal x2 of n, pass through a system and get the result y2 of n. Now if I combine these two signals at the input side, first I have applied separately on the system. If we combine these two signals, sum these two signals here, x1 of n plus x2 of n, and apply it to a system, the output is y1 of n plus y2 of n. This property is known as the additive property. I have first given to a system a signal separately and then combine these two signals and send at the output. I will get the combination of the both output, these output. So this is known as the additivity property. I have also already explained these properties, additivity and homogeneity. Now the third is time shifting. This is not important for a linear system. For a linear system, these two properties must satisfy. But what about the shift invariance? Shift invariance is important in concept of DSP. For DSP point of view, shift invariance is important. All the signal we deal in DSP, detailed signal processing, all we use the signal must satisfy the shift invariance property. Otherwise, the signal processing is not possible. What is shift invariance? Shift invariance is nothing but a signal that does not depend upon time. Let's see with the help of an example. Let's suppose we have signal x of n and pass through a system and get y of n. Now this signal, if we have shifted the signal x plus 3, now if we shift the signal and pass through the same system, then we will get y of n plus 3. So the shift is same in the output as we have applied to the input signal. So this is shift invariant. This is not important. I am again saying this is not important for linear to system to be linear, but this is important if we are dealing with linear system in DSP. Then this property is important to satisfy our requirement and our techniques that we use in DSP. System must have this property because when we dealing with signal, there is some delays in signal. We send one signal from one place to another, there are some delays. So if this property is not satisfying, then we have not our required output, wrong output we will get. So this is very important in DSP point of view. Although linearity is, these two conditions are important for linearity. And if we are dealing with linearity, why we have not these property not satisfied linearity? Because shift linearity is something bigger concept. There are in linearity there are many other concepts. Further linearity is divided in basic. If we are dealing with homogeneity and additivity, there may be another field, some other field not related to the system. So if we are dealing with system in DSP, then we have to combine this property with these two properties. Now the other concept is static system and sinusoidal fidelity. So what are static system? Let's suppose the system like y of n is equal to 5. These are constant system. This is we will say that these are static system. No matter what we have applied to input signal, the result will remain the same, 5. So there is input is not depending upon the output. Output is a constant number. So these are static system. The graph of these system are like this. If this is x-axis and this is y-axis, then the graph of these static system are like this. This may be some value 5. Let's say I have written this. This is y of n, or we are not using a discrete system. I am in this example I am using a, so the notation is this, and we can use here also y of t, and this is x, long axis is y axis, so this value is 5. So no matter what we apply the value of x here, at x is equal to 1 it is 5, at x is equal to 5 it is 5, so it is not changing. So this system is a static system. And the other is sinusoidal fidelity. What is this term sinusoidal fidelity? Let's suppose if we have a system, if we have applied some input and get some output, the output is y of n and signal is x of n. Let's suppose this signal has a frequency of f1, and this is the signal. This is not in continuous domain, but rather it is in discrete domain, like this. This is discrete signal, and we get an output y of n having the same frequency. Frequency is not changing, and the output is again like this, or it is a scaled version of some output signal. I will draw this much larger so that you can see that it is scaled output like this. So the output is nothing but a scaled input signal, but the frequency will remain the same. So this property that the system will not change the frequency is known as the sinusoidal fidelity. And this sinusoidal fidelity always true for linear system. Linear system always sinusoidal hold sinusoidal fidelity. So this is all about static system and sinusoidal fidelity. now we will study about some example of linear and non-linear system. First we will discuss their graph. How does linear system look like and how does non-linear system look like? So always the linear system, if we see their graph, they are always a straight line, like this line, like this line. This line may be V is equal to IR, Ohm law, or F is equal to Kx, Hooke's law. So these are an example of linear system, and always if we see their graph, they are straight line. They are nothing but a straight line, like this line. They are infinite line, so you can draw here. So they are always like a line. So if we see the graph of non-linear system, they are maybe curved like circle, and there are many like loop shape. They are always non-linear. The graph other than a straight line are always non-linear system. Like this graph is non-linear. It is the function of diode with current and voltage. This is voltage and this is current. So operation of diode is a non-linear behavior, and this is hysteresis loop. When we apply a magnetic field on a conductor, so its domain are aligned in this way. This is graph of their domain alignment, so that the iron become conductor. This is the graph of hysteresis loop. And if we see the example, like wave propagation is a linear system. Example of linear system, electric circuit that we have discussed. Ohm law is here. Mechanical system like F is equal to Kx. The expansion and compression of a mass spring system or any other system, if we apply a force on a spring, it may compress or expand. That is explained by this equation, Hooke's law. And another example is multiplication of a scalar, like we have seen homogeneity property. Homogeneity property is nothing but a multiplication of a scalar. We multiply some input signal with a scalar, and at output we will get a scaled version of output. So this is nothing but a homogeneity property, but linear system have the property. And null system and unity system. What is null system? Which has no output, zero output, is known as null system. And unity system is also like that, we have output equal to 1, so we can set that unity system. They are always linear system. Now coming to non-linear system, we have power dissipated in a resistor. The power dissipation in a resistor is a non-linear behavior. As the temperature increases with the passage of time, the more power is dissipated in a circuit. We have equation P is equal to V square over R, or P is equal to I square R. So the term involves square. If we have in equation we have power greater than 1, the system becomes non-linear. So power dissipation in a resistor or in any electric circuit is also a non-linear behavior. The second one is signal multiplication. Multiplication of a single signal with another signal is also a non-linear system. We have one or two cases here. Let's suppose one signal is a linear signal, and other is also a linear signal system. So if we multiply both the signal, then we again get the output non-linear system. So if we have one non-linear system and one linear system, again we get non-linear. So how we can get is always multiplication of signal with either it is non-linear or linear, we will get again non-linear system. And hysteresis is that we explained in this, already explained. And function of diode is also a non-linear system. Now we will discuss some property of a linear system and we will see how we could recognize that the system is linear or non-linear if we have a complex system. So first of all, the property is commutative. What is commutative? We have studied in our previous classes that a plus b is equal to b plus a. This is, we have studied in our math classes that this is commutative property. If I replace this equality sign with an arrow, so not with an arrow, if we represent, let's suppose that a and b, these two are system. We have input signal x of n, and here we have some system, let's say a. We name that system is a, and the signal passed through a system, and then the output of a system passed through the b system, and then we have final output y of n. Let's suppose this is an intermediate output v of n, v1 of n. If we have two systems a plus b, and the signal first passed through a system and then b system, and then we get the output. If we change the order of the system, let's suppose we change this order, like we have first signal b and the second signal is a. Then we again get, if we pass through the same input signal, we get the same output signal. But the intermediate signal may change. It may be v2 of n. It is not the same because the functions are different. So this signal may change, but the final output will remain the same. This is known as the commutative property in linear system. Now coming to our complex systems, these blocks, K blocks, are all systems. So how we could recognize this is a complex system? There are 3 input and 3 output, and many summation sign and many system. So these, it is not compulsory that this complex system are always non-linear system. It may be linear system. We will check this how we can recognize it. So we will see that if all the signal, let's suppose that x2 of n are summing in first branch, not multiplying, they are summing. So by summation sign we can recognize that this output is linear output. And again, if we see the second branch, this a plus b, here what signal is a plus b, and a plus b is again adding with c, a plus b plus c, so it is again a linear system. If linear system are summing together, their result always be a linear system. So here again, if we see that x3 of n passing through a system D, and x2 of n is adding here, and not multiplying, adding here, and E again this signal is adding here, so it is combination of all these system is a linear system. Let's suppose we don't have a summation sign here. If we remove the summation sign, if we multiply these signals like this, and these two signals are multiplying here we have not, or we can replace this sign with a multiplication sign, though they are not summing but multiplying. So we already studied that multiplication of a signal with another signal is a non-linear system. So this becomes non-linear system. So this whole complex system becomes non-linear. If one of the branch is non-linear, one of the multiplication sign appear, the whole system becomes non-linear, because we are seeing as a whole. So the whole system is non-linear. If we replace this sign with the summation sign, we can also use this sign. This is summation sign, or we can use plus sign. So now this system is linear system. Now we will see superposition in DSP. Superposition is very important in DSP. We'll see this in this lecture. What is superposition? We already studied that superposition is nothing but satisfying the two property by a system, which is first one is homogeneity and the second one is additivity. And this is this is the properties of linear system. And again, linear system must satisfy superposition theorem. So these all things are interrelated. Superposition is nothing but satisfying two property, additivity and homogeneity. And this is also the requirement we have studied, the requirement of linear system. So linear system must satisfy superposition in short. So superposition, we will revise this concept. What is superposition? Superposition is nothing but scaling some, let's say, a of x1 of n. I have taken one signal and scaled with the factor a, and then perform the submission and again take the scaling factor b, and again the signal is x2 of n. I have passed through this system and get the output a times y1 of n plus b of y2 of n. We are familiar with this equation. We already studied this equation. So what is this happening in this equation? We are scaling the signals and summing the signal and sending to given as input to a system, and the output will get, for output x1 of n we have y1 of n, for input signal y2 of n we have y2 of n. We are again getting the scaled version and submission of these two signals. So this is all linearity all about. So if we can, what superposition says, that if we can combine these signals and get the combination of a signal, so we can also decompose the signal into a simpler component. Let's say we have a signal that is complex in nature. I am giving example in continuous domain so it is easy to understand. Likewise, if I have a signal like this, so it is a complex signal. It is not a simple sinusoidal with a single frequency signal. It is not a single sinusoidal signal with a single frequency. Rather, it is a complex signal. So we can decompose this signal into its component, simple component, like we can use different sinusoidal, different frequencies of another signal with this frequency, and summing many sinusoidal signals with different frequencies, and we may get this signal. So complex signal converting into a simpler signal is known as the decomposition process. What is known as decomposition? Decomposition of a signal. The question is why we are decomposing the signal, why we are doing this signal? Because in DSP we have to process signal, and it is easier to process simple signal rather than a complex signal, because for complex signal we design the receiver or whatever the component is, it will make complex and it is costly. So the technique we are using here, we are converting the complex signal into a simple signal, so our the system become less complex, simple, and we are performing the same operation as we have. We are getting the same information as we have from this signal. We are getting the same information from both the signal, and it is easy to divide larger problem into a smaller chunks and solve their chunks one by one, and it is easy. So this is all about the decomposition process, and there are many type of decomposition in DSP. We will study it one by one. The first one is impulse decomposition, the second one is step decomposition, again even and odd decomposition, interlaced decomposition, and Fourier decomposition. The impulse decomposition and the Fourier decomposition are very useful decomposition processes, very useful, and these three may be sometimes used and sometimes not used. They are not very common, but these two processes, especially impulse decomposition, is the core, what I say, the core of DSP. So it is very important. Impulse decomposition is very important. Fourier decomposition deals with analog signal. In DSP we are dealing with data system, so we not use Fourier decomposition as much, but we can use Z transform, which is same as the Fourier but in discrete domain. So we will use that later. So these are all decomposition types of decomposition. Now we study it one by one. The first type is impulse decomposition. So how we can decompose a complex signal into a impulse signals? So we will see with the help of an example, then it will be clear to you. Let's suppose I have a discrete signal, like this is my zero index value, and it is 1 at 0, and it is 2 at -1, and at 2 it is 2, and the other values are 0. So this is not a complex signal. This is just for example. I am saying that this is some like complex signal. So we can decompose this signal into a simpler signal. So how we can do this? We can do this. Let's suppose we decompose operation is applied, and we can split this signal into a impulses, scaled impulses, and by summing all these signals we again get this signal. Let's see how it works. The first signal I will take is, this is my zero index value. The first signal I have -1 and value is 2. At -1 value is 2. So it is nothing but an impulse signal which is shifted to the left side and scaled by 2. Let's suppose this is x of n, and this is, if we write it, it is delta, not g, it is delta of n plus 1, and it is scaled by 2. So it is a shifted and scaled version of impulse signal. What is impulse signal? At 0 we have a peak 1 and all other values are 0. So it is nothing but a shifted and scaled version of impulse signal. And we have 2 more peaks, so we can write 2 more signal here, impulse signal. The other signal is, at 0 we have value 1. At 0 we have value 1. And it is nothing but delta of n, because at n it is 1 and all other values are 0. These are 0 values till from infinity to minus infinity. So if we want to complete this signal, I have another 1 peak at x is equal to 1, at n is equal to 1, and the value is 2. So again I have signal at x is equal to n and 1. I have peak of 2, and here it is at -1 it is 0, and continuing the 0, and on the right side 0 0. So it is nothing but a shifted and scale, also shifted and scale version of delta of n -1, and it's scaled by 2. So by summing this signal, what we get? Let's forget this signal. I have drawn these 3 signals. Let's sum this signal. What we will do at -1, all the values, we take the sum of all the values. It is 2, it is 0, 0. So what we get? -2. So if we draw this signal at 0, at -1, and at not -1, at 1, and all other values. So at -1 it is 2 plus 0 plus 0. Again we will get 2. And at 0 index, what is it? Is 0 plus 1 plus 0. Here we get, and again at 1 this is value 1, this is 0, again here 1 0, this is minus 1, this is 0, and this is again 2, and what we will get is 2. So we get by summing this signal, what is this signal is, this is 2 into delta of n plus 1 plus delta of n plus 2 into delta of n minus 1. So I have take the summation of all these signals. This is nothing but 2 into delta of n plus 1 and all these signals, and we get this. But this is nothing but the same, this complex, I am saying for example this complex signal, this is nothing but a complex signal. So what we have get, we have this complex signal is x of n. So we have reduced or decomposed this x of n into a shifted and scaled version of impulse signal. The complex signal is decomposed of this impulse signal. This is known as the impulse decomposition, and it is very important for DSP point of view. We have taken a complex signal, decomposed it into a series of impulse signal, shifted and scaled impulse signal, and if we add this signal we get the same signal. So what we get, that x of n is nothing but a shifted and scaled version of all that impulse signal. So this is the impulse decomposition. Now the another type is step decomposition. What we will do in step decomposition, like we have done in our impulse decomposition, we have converted the complex signals into a series of scaled and shifted version of impulse signal. Now in steps decomposition, what we will do, we will take a complex signal and convert it into a series of step signals, and we will see this with the help of an example. I am taking the same example for my convenience. So this is not again a complex signal, but we are rather assuming this is complex signal, because for a complex signal we have to do a lot of work. So if we apply the property to a simple signal and show that this is happening true, so we can also apply on larger scale. But for this lecture I am assuming this signal to be a complex signal. So what we will do to decompose into a step signal, I am taking first this is 0, this is 0, this is 1, this is 2, and so on. It is continuing, and it is 0, it is minus 1, not 0, it is minus 2, and it is also continuing. So first the impulse we have at minus 1. So at minus 1 I am taking this 2 and continuing this forever till infinity. What is step signal? Step signal is when n is less than 0, it is 0, and when n is greater than or equal to 0, it is 1. So likewise I am scaling these all equal to 2, and this is continuing till infinity, and this is. So if we see this signal, it is nothing but a scaled and shifted version of unit step signal. If we write this in the form of equation, what we will get, 2 is a scaled version, because unit step we have amplitude of 1, it is 2 amplitude, so it is scaled by 2 into u of what we'll say n plus 1. So it is a shifted and scaled version of unit impulse signal. So it is for first peak, not for all signals. So I will draw another signal at 0, its value is 1. So at 0 it is 1, and I am continuing these till infinity, and it is 1, it is 2, it is 3, and here minus 1 it is 0, and minus 2 it is 0, and it's continuing here. So this is nothing but a simple unit step signal. If we continue this at index 1, we have value 2, and again we get, here we have 0. We'll take this minus 1, we will take this to 2 and continue this 2 till infinity. This is 2, this is 3, this is 4, and this is continuing. Here it is minus 1, minus 2, and it is continuing till infinity. Here we have 0 values. So we have decomposed a complex signal into a shifted, what we will say, this is u of 2 into u of n minus 1. This is again shifted and scaled version of unit step signal. So we have converted a complex signal, assumed a complex signal, into a series of scaled and shifted version of unit impulse signal. So our next type is even and odd decomposition. This is not very important decomposition. In this decomposition, a complex signal, a combination of even or odd signals, are decomposed into its component even and odd signal. So in this I have taken some complex signal, so I can convert this signal into odd and even signal. So it is a combination, it is neither even nor odd. So the formula for even and odd decomposition, we have already studied that for even decomposition, if we want to take the even part of a signal, what we will do, we have a formula, let's say x of n, this is x of n, and we want x of n e mean even part of that signal. So x of en is equal to x of n, we will take x of n and plus that signal with x of minus n, the reflected or flipping version of that signal, and divide it by 2. Then what we will get? The even part of this complex signal. So how we will get the odd part? For odd part, I have written that O for odd part, x of n is equal to x of n, x of minus n, this reflected or flipped version of that signal, but this time we will minus this shifted impulse signal with this, and we will divide by 2. By using these two formulas, we can decompose this complex signal into its component even and odd signal, because this is a composite signal, combination of both signals. So we will decompose into its two components. So the reflected version of this signal I am drawing here, and we will draw the even and odd part here. So the reflected version is, for reflected version, not is equal to, let's say this is here, the reflected version is nothing but the values at this side will get into this side, and these values goes to another side. The flipped version, mirror image of this signal about y-axis, is the reflection of the signal. So at 0 will remain the same 1, but this value will come to this side. So at minus 1, minus 1, minus 2, and this is 0, 1 and 2, and this is 0, and it is continuing here. So at here it is 1, it is 2, it is minus 1, minus 2, and the value of at 2 is 2, so at minus 2 it is minus 2, not 2, minus 2. So at 1 it is 2. So these two will go to another side, and this will become 2 and 2. So this is a reflected version of this signal. Agree with me? Now what we are doing, we are adding these two signals and dividing by 2. We will get the even part. So if we perform these operations on these two signals, adding and dividing by 2, what we will get at -2, it is 2, value is -2 and its value is 2. So 2 minus 2 is 0, and then dividing by 0 by 2 is again 0. So at -2 we will get 0. And at -1 it is 2. At -1 it is 2. 2 plus 2 4, and dividing by 2 it is again 2. So at -1 its value is 2. Now at 0 we have 1 and 1. So 1 plus 1, what we will get? 1 plus 1 2, and dividing by 2 again we get 1. So here we at 0 we have 1. Likewise at 1 we have 2, and at 1 we have 2. 2 plus 2 is equal to 4, and dividing by 2 is again we get 2. So at 1 we have 2, and again at 2 it is 0. Look here, 2 minus 2, 2 minus 2 0, divided by 2 again 0. 0 divided by 2 is 0. So the signal that we get here is nothing but a even part of this signal, even part of this signal. We have decomposed even part from this complex signal. So how we will decompose into the odd part of this signal? We will minus this signal into this signal and divide by 2 using this formula. So here at -2 I have 2. 2 minus into -2 is plus 2. 2 minus into -2 is 2 plus 2, and it is 4, and dividing by 2 again we get here is 0, -1, -2, 1, 2, it is 0, it is here again 0. So I have value 2 minus -2 plus 2, and divided by 2 we will get 2. 2. I have this at -2, I have 2 value. At -1, 2 minus 2 is 0, and 0 divided by 2 is 0. So at -1 I have 0 value. And at 0, 1 minus 1 divided by 2 is 0. So again we get 0 value. And at 1 we have 2 minus 2 divided by 2 is, using this formula, is 0. So at 2, here we have -2, and here we have 2. To -2 we will get a -2 of this and minus of this formula, and the value of this is again 2, and divided by 2 using this formula, x of n value and minus x of minus n value, and divided by 2. So we will get 2 minus 2 minus 4 divided by 2, and the final answer is -2. So we will get -2. So this signal that we have get is the odd part of the signal. If we combine or take the sum of these two signals, we will again get the same signal. Let's sum this out and see what will happen. Sum these two signals, what we get at 0, it is 1, because 1 plus 0 is 1, and here 2, here 0, at 1 it is 2, and at 2 what its value is? -2, because -2 plus 0. Here it is at -1, it is again 2, and at -2 again it is 2, and 0, 0, and continuing, and it is also continuing 0, 0. So the sum of these two signals, this even and odd part, it is nothing but x of E of n plus x of O of n. I am summing this even and odd part and getting the same result of this complex signal. So I have decomposed this signal into even or odd part using this formula. This formula is for getting even and odd part of the signal. And again, summing these two things, we will get again. This is known as the even and odd decomposition of a signal. Now the second last type is interlaced decomposition. This is also not very useful decomposition, but we are studying this because we are studying DSP and these are some basics, so we have to know what are these concepts, interlaced decomposition. So for interlaced decomposition, I have written this x of n signal, for example. And what in interlaced decomposition, what we are doing is at even indexing, first we are supposing that at even indexing we have zero value. Okay, assuming. So if we write this signal, I am assuming that value is 0. So at -2 it is even, here it is 0, we will not consider these value. Here 1, -1, -2, here it is 1 and 2 and 3 and so on, they are repeating, here -3. So we are assuming that at even indexes the value is 0. So -2 is even index, we suppose that its value is 0. We are not taking this value, we are supposing that at even indexes the value is 0. So we are taking this 0. And -1 is odd index, so we will take this value. This is -2. Not -2, it is 2. And 0 is again even, we consider it 0 even. So at even index we are assuming that 0 value. So 0. So at 1, what we are considering, 1 is odd, so we are taking this value 2. This. At 2, it is even index, so we are supposing that its value is 0. So at even indexes, we have taken the value 0. And other than even indexes, like odd indexes, we have taken value same that are given in our complex signal. This is a part of decomposition of this complex signal. Another part, we are doing the inverse process. What inverse process? That we are taking at odd indexes the value is 0 and at even indexes the value we will take is from this complex signal. So at -2 it is even, so at -2, -1, 1 and 2. So at -2 it is even index, so we will write it 2. And -1 is odd index, we will take 0 value, and 0 is again even, so we are taking the value of -1, oh not -1, 1, sorry. And at 1 it is odd, so we are assuming that it is 0, and at 2 it is -2. So what we have done here in interlaced decomposition, we are first taking the even indexes 0. The value of even indexes is 0 and written the complex, modified complex signal, modified form of complex signal. And in the second time we are assuming that at odd indexes the value is 0 and other values we take from this complex signal, and we have write these two signals. So we have decomposed this complex signal into two signals, this and this, and the combination of these two, if we sum these two, will get again this by summation. So we have decomposed this signal. There are what we want to do is to reduce the complexity. They are reducing the complexity. Although they are not very convenient and not very accurate and not very useful, but these are some methods that was designed earlier. They are, in some cases they are useful, but they are not very useful in every system. So we have to study it, whether they are useful or not. So again, this complex signal we have decomposed into two signals, and by summing these we will again get this signal. So it means that these two are the decomposition form, or component of this complex signal. The last type is Fourier decomposition. Fourier decomposition deals with analog systems, and the Fourier decomposition is very important in analog system. So we will see the next form of Fourier transform to be a Z transform that we use in discrete system, and we will also use in DSP. But what is Fourier transform? So to explain this Fourier transform, I will use analog signal, because Fourier transform deals with analog system. So I am considering here with example an analog system and analog signals. Let's suppose I have a signal that is complex, very complex, and here it is not a signal of single frequency, single sinusoidal. It is not. It is very complex signal. So by decomposing this signal, what Fourier said, the Fourier decomposition is named after the scientist Fourier, that told us about that every complex signal, every analog complex signal can be converted into a simple sine signals with different frequencies. So by decomposing this, we have a series of many signals. Let's say n number of signals. There are many signals, but with different frequency. They all are sine signals, sinusoidal wave, but different phases, different amplitude, and different frequencies, and we will get this signal. Let's suppose those signal, one is with this frequency, let's say f1, phase is 0, phase may not or may not be changed, may change or may not be changed. With frequency f1, this is a sine wave, and again the other may be like this, with higher frequency f2, and the third component may be much smaller frequency, and the third one with different frequency, and the fourth one is different frequency. There are f3, f4, and fn. There are infinite signals in between, not infinite but many signals. So to decompose a complex, very complex signal, this is very complex signal, so we need many number of sinusoidal waves with different frequency and amplitude and different phases. So by combining these signals we will get this complex signal. So it is difficult, again I am saying it is difficult to recognize this complex signal. We will take the example of voice signal, telephone. If we are sending our voice signal, this is not a single sinusoidal wave. Sinusoidal wave has no information. So our voice is like this, a combination of many. This is a combination of many sinusoidal signals. So what we are doing in our systems, we are converting this complex signal into a series of simple signals and then sending. What is benefit of this? At receiver, in channel we may have different noises, so our signal may become like this. So how we reconstruct this signal from this? It is not easy. So what we will do, we will convert this complex signal to a simple sinusoidal, and we send this through a channel, and at receiver end we will combine all these frequencies. In these frequencies we get noise. This may be some like this type of noise. So we can regenerate into a simple like this. We can regenerate this simple sinusoidal signal, but we cannot regenerate this complex signal at receiver. So at receiver, if the signal is noisy, we will convert into sinusoidal signal. The component which is affected by noise, we will again regenerate it. and again sum all the signals, n number of signals, and we will again get this voice signal. So the decomposition has lot of benefits. All the applications around us that we are using, calling, mobile phone, all depends upon this decomposition processes. So I think you have learned this concept of decomposition, and Fourier is the most common and important concept in analog domain, and in digital domain we deal with Z transform, and we will study that later in next chapter. The last topic of this chapter is alternative to linearity. What this means? Alternative to linearity. Why we need this alternative to linearity? Because in DSP, all the system we have are dealing with linearity. Linearity is very important. So some in our physical phenomena, some of the signals are not very exactly linear system. There may be some we can do some approximation on systems, and we can say that these signals are approximately linear. That what we called alternative to linear. I am giving an example with the help of a graph that you can understand it easily. Let's suppose I have a signal, and this is our response of a system. So although this is not linear, this is not a straight line, and I told you that the linear system response is a straight line. This is not a straight line, rather it is a like a sinusoidal component including in this signal. But what we are saying, we saying that approximate these values, that some upper and lower values, to a single line. We are approximating these values in upward and also in downward, and we are replacing these sinusoidal component into a single line, so to make this system a linear system. So with this advantage, we have some noise, some distortion, but we can use this signal in our real life. So this is not very accurate method, but we can use many algorithms and filters to apply these concept. So it is better than nothing. It is something is better than nothing. So to use these signal, we are applying the concept of linearity, alternative to linearity, so that we are saying that it is approximately linear, so we can use these signal into a real life. Now our lecture has come to an end. We have studied chapter number 5 of the book, so we'll